Welcome back to Rice.AI Code Room. Today we are tackling LeetCode 3548 equals Sum Grid Partition II. This is a fascinating problem that tests our ability to manipulate grid partitions and understand topological properties like connectivity. Let's dive right in and break this problem down step by step. Let's carefully read the problem statement. We are given an m by n matrix filled with positive integers. Our goal is to make exactly one horizontal or one vertical cut to split this grid into two non-empty rectangular sections. But here is the catch: we want both sections to have exactly the same sum. Now, if the sums are already equal, great. But the problem gives us a powerful tool. We are allowed to discount, or remove, at most one single cell in total from either of the two sections to balance their sums. However, there is a very strict rule for this removal. The remaining cells in the section where we removed the cell must stay connected. This means we can't just pick any random cell if it breaks the section into two separate pieces. We need to return true if we can achieve this equal sum partition, and false otherwise. Let's look at a concrete example. Imagine a 2x2 grid with values 1, 2, 3, and 4. If we make a vertical cut down the middle, the left section has 1 and 3, summing to 4. The right section has 2 and 4, summing to 6. They are not equal. But, if we remove the cell with the value 2 from the right section, its sum becomes 4. Now both sections have a sum of 4, and the remaining cell 4 in the right section is technically still connected since it's just one cell. So this would be a valid partition. To solve this efficiently, we cannot afford to recalculate the sum and check all removable cells from scratch for every possible cut. This would lead to a time limit exceeded error. Instead, we need a sweep line algorithm. Think of it as sliding our cut line from top to bottom, row by row, for horizontal cuts, and from left to right, column by column, for vertical cuts. As we sweep this line, we dynamically maintain the total sum of the top section and the bottom section. But sums are not enough. To know if we can balance the sections, we must know what exact values are available to be removed. So, we maintain two frequency arrays, frequency_top and frequency_bottom. When we move our horizontal cut down by one row, we simply add the values of that new row to frequency_top and subtract them from frequency_bottom. We also update the sum_top and sum_bottom accordingly. This allows us to update our state in order of the number of columns, making the sweep highly efficient. If sum_top is greater than sum_bottom, we need to find if there is a cell in the top section with a value exactly equal to the difference. We can instantly check this using our frequency_top array. Now, let's talk about the most crucial insight of this entire problem, the part that trips up most people, the connectivity rule. The problem states that the section must remain connected after removing a cell. Let's analyze the shape of our sections. When we make a cut, the resulting sections are always rectangles. If a rectangular section has at least two rows and at least two columns, it forms a 2D grid. The mathematical truth is, you can remove any single cell from a 2D grid of size 2x2 or larger, and the remaining cells will always stay connected. There are no choke points that a single cell removal can break. However, what if the section is just a 1D array? That is, it has only one row, or only one column. In a 1D line, every middle cell is a critical bridge. If you remove a middle cell, the line snaps into two disconnected pieces. Therefore, for a 1D section, you can only ever remove the two cells at the very ends. This observation is the absolute core of the algorithm. We don't need to run complex graph traversal algorithms like depth-first search to check for connectivity. We just look at the dimensions of the section. Let's see how this brilliant insight translates into elegant C++ code. First, we calculate the total sum of the entire grid. Then, we begin our horizontal sweep. For each row split, we update our sum_top and our frequency arrays. We calculate the absolute difference between sum_top and sum_bottom. If the difference is 0, we immediately return true. If the difference is non-zero, we check which section is larger. Let's say the top section is larger. We then check its dimensions. If the top section has at least two rows and at least two columns, it's a 2D grid. We can safely remove any cell, so we simply check if frequency_top difference 0. But if the top section has only one row or one column, it's a 1D line. We cannot use the frequency array anymore. Instead, we must explicitly check only the boundary cells. We check if the very first cell or the very last cell of that 1D section equals the difference. We repeat this logic for the bottom section, and then we run a completely symmetric vertical sweep from left to right. This clean logic handles all edge cases gracefully. Finally, let's wrap up with the complexity analysis. For the time complexity, calculating the initial total sum takes big O of m times n time, where m is the number of rows and n is the number of columns. Our horizontal sweep visits each row and iterates over its columns, which again takes big O of m times n. The vertical sweep is symmetric and also takes big O of m times n. Therefore, the overall time complexity is strictly big O of m times n, which is optimal because we must process every cell at least once. For the space complexity, notice that the problem states cell values are up to 100,000. We use fixed-size frequency arrays of size 100,001. We do not allocate any dynamic 2D matrices for the sweeps. Thus, our space complexity is big O of 1, strictly speaking, or big O of the maximum value v. This is extremely efficient and guarantees our solution will easily pass all test cases. Thank you for watching Rice.AI Code Room. Don't forget to like and subscribe for more deep dive LeetCode explanations.